Hello everyone, thank you for joining us. My name is Shivansh Srivastava and this work is done in collaboration with Dr. Bappaditya Mandal and Dr. Anirban Chakraborty. And today we are going to be talking about HFCER, which stands for Hybrid Fusion for Cultural Event Recognition. The research in image understanding domain is moving towards tasks that require reasoning about concepts that carry more semantic meaning rather than just visual similarity. Event recognition in images is one such task. In this work, we propose HFCER, a hybrid fusion technique used to combine early and late fusion strategies into a single model. We also propose an alternative training scheme to train the proposed HFCER network. We also support our hypothesis that complementary object and scene information is available in early fusion technique using image activations generated using guided backpropagation method. Learning complex, high-level semantic concepts about objects, seen, and their interactions in images would require a huge amount of data. However, the datasets available for the task of event recognition are quite small compared to other well-studied tasks like object and scene recognition. Also, images belonging to same event class can appear quite visually dissimilar, leading to high intra-class variability. On the other hand, images belonging to some subset of different event classes could appear very visually similar despite belonging to different event classes. The techniques used in literature for event recognition in images span a wide variety of models, starting from variational message passing based on coupled latent Dirichlet allocation. Also, some other techniques used AlexNet along with multi-scale spatial maps generated by object face and human detector. Wang et al. Used ensemble of six Inception V2 models pre-trained on ImageNet and Places datasets. The six models were trained on different transfer learning techniques, namely initialization, knowledge-based transfer, and database transfer. Before studying different fusion techniques, first we need to prepare the deep nets which will be used for extracting image and scene representations. For this, we use ResNet 50 architecture which is pre-trained on ImageNet and Places 365 datasets. The extracted features from these two architectures will be given as input to the fusion networks to predict the event classes. For the rest of the presentation, ImageNet pre-trained event fine-tuned models will be denoted by O2E-CNN, which stands for Object to Event CNN, and Places 365 pre-trained event fine-tuned models will be denoted by Scene to ECNN, which stands for Scene to Event CNN. We use average fusion as the choice of our late fusion technique. In this technique, the probability score of each class is calculated by finding mean score of that class across all the predictors. To alleviate the issue of having information of only single domain until after performing late fusion at final prediction level, we perform early fusion at representation level where we concatenate the object and scene representations and apply batch normalization over it. Despite its simplicity, effectiveness of using concatenation for early fusion is observed in several tasks such as segmentation of urban images, face recognition, etc. Now that we have combined object and scene representations using early fusion, we hypothesize that complementary scene and object features from dedicated networks are utilized by early fusion techniques. For a qualitative study, we analyzed the image region activations generated by using guided backpropagation method on both the models O2ECNN and S2ECNN. In these activations generated using guided backpropagation method, we see that in case of early fusion, the object pre-trained networks show activations on foreground images such as sculpture in case of first image and the foreground faces in case of second image. Similarly, in case of scene trained networks, the activations are shown for background objects such as fence or person in the first image or the background trees in the second image. However, in case of late fusion, we see that the activations span over whole images, as we can see in the first and the second case. We attribute these observations to the fact that both object and scene features are needed for differentiating between various event classes. In order to achieve this in case of late fusion, both object and scene pre-trained networks try to learn the missing information from the event classification datasets while fine-tuning. However, in case of early fusion, the information is available from dedicated sources which can be utilized, and hence we observe complementarity in observations. In order to combine the capabilities of early and late fused models, we propose a hybrid fusion technique as a combination of early and late fusion techniques. We call this technique HFCER, which stands for Hybrid Fusion for Cultural Event Recognition. In this model, the representations generated from ImageNet pre-trained model and scene pre-trained model are combined using early fusion to give a concatenated representation, which is then followed by dropout and fully connected layer to output event probabilities from the early fused representation of object and scene features. Also, these individual representations are followed by dropout and fully connected layers to give out event probabilities that are trained on each of these individual representations. Finally, to combine all these three event probabilities, we use average fusion to give out final event probabilities. The loss function used for training this model is added cross entropy for each of these three event probabilities, which are given as output of early fusion model and individually fine-tuned models of each of these object and scene representations. In the HFCR model discussed in previous slide, all the parameters are tuned simultaneously. By all the parameters, we mean the parameters of the early fusion network and the parameters of the individually fine-tuned networks. There are some certain drawbacks to this situation. For instance, parameters of all the three models increase the dimensionality of the problem whilst keeping the number of data points constant. Also, simultaneously optimizing all our parameters increases the memory requirement during training because gradients of all the parameters are needed to be kept in memory simultaneously during each gradient update. To alleviate all these drawbacks in HFCER, we propose an alternating training scheme for training the hybrid fused models. In the proposed alternating training scheme, we train the base models and early fused model alternatively in each epoch. While training the base model, the loss functions used are just addition of the individual loss functions, which are cross entropy losses. Since we are just adding the loss functions for each model in the late fusion part, during backpropagation, the gradients applied in each of the base network are dependent only on its own parameter and not on the other base network's parameters. This is because differentiation is distributive over addition. While training the early fusion part, the gradient updates for only the parameters of early fusion network are generated and the rest of the parameters are kept constant. In the block diagram shown here, the freezed parameters are represented by blue and trainable parameters are represented by orange across alternate epochs. In the epoch when early fusion parameters are kept freezed, the loss function is formulated by adding cross entropy losses from event class predictions generated by O2E and S2E CNNs. The loss calculated from O2E event class predictions is only dependent on parameters of ImageNet pre-trained base network and fully connected layers trained on top of the extracted object representation and is independent of the parameters in S2E CNN. A similar argument of independence could be made for scene representation and O2E CNN parameters. Now that parameters of O2E and S2E CNNs do not affect each other's loss functions, the gradient updates calculated during backpropagation are calculated as if these models are trained in isolation with each other. By this, the number of parameters that are needed to be optimized simultaneously are mathematically same as the case when these two networks are fine-tuned individually in the late fusion case. In the next epoch, we freeze O2E CNN and S2E CNN parameters that we kept trainable in the last epoch and set parameters of early fusion network to be trainable. As only the early fusion network parameters are being trained, this is less than the parameters in the early fusion case that was depicted in the earlier slides. To evaluate our results, we use Chalearn looking at people event recognition dataset and web image dataset for event recognition. All models are trained in PyTorch using gradient descent optimizer with 0.001 learning rate halved every 65 epochs and zero point 0.1 momentum for 250 epochs. We use multi-scale multi-ratio augmentation proposed by Wang et al. During training and testing phase. We show state-of-the-art performance on Chalearn looking at people event recognition dataset by combining results of HFCER, late fusion, and early fusion networks using average fusion. Also, HFCER trained using alternating training scheme performs at par with state-of-the-art methods whilst using significantly lesser number of models. Also, HFCER models with or without alternating training scheme perform better than early and late fusion techniques, which were said to be the baselines for the proposed hybrid fusion technique. Significance of the use of alternating training scheme is evident from the increase in performance observed in HFCER by using alternate training instead of simultaneous training of parameters. In case of wider dataset, our method gives better performance compared to all other neural network-based end-to-end trainable models. The method used by Ahmed et al. Uses particle swarm optimization to learn late fusion weights over SVM-based predictions using features extracted from ImageNet and Places 365 pre-trained CNNs. In contrast, our method uses a much simpler late fusion technique and is end-to-end trainable. In this work, we aim at identifying effective strategies to intelligently combine information cues from object and scene representations available using deep learning models for aiding the task of cultural event recognition in still images. We study the use of early and late fusion strategies to combine information extracted from deep neural networks pre-trained on ImageNet and Places 365 dataset. The use of late fusion allows the classifiers to reason about cultural events based on a single modality of information available to each of the classifiers. The motivation of using early fusion of representations was to allow the event prediction model to simultaneously harness information from object and scene cues in a complementary fashion. As a qualitative study of this hypothesis, visualization of image level activations is performed for early fused model as well as its individually fine-tuned counterparts, which are used for late fusion and are trained on a single modality of information. The visualizations show accentuated complementary activations on foreground objects and background scenes in case of early fusion model. On the other hand, models fine-tuned using unimodal information show no such behavior. We propose HFCER as a way to combine early and late fusion into a single architecture and propose an alternating training scheme to effectively train the HFCER architecture. The proposed hybrid fusion technique performs better than the early fusion and late fusion baselines and at par with the state-of-the-art models whilst using significantly lesser number of models than the current state-of-the-art. Also, the proposed alternating training scheme results in improved performance and reduced memory requirement for training hybrid fusion networks. By using late fusion of HFCER, early and late fusion techniques, state-of-the-art performance is achieved on Chalearn looking at people cultural event dataset. HFCER along with alternating training scheme could be used as a general fusion strategy to aid several computer vision tasks other than classification such as CBIR and person re-identification where information fusion is being actively used by the research community. Thank you all for your attention and have a nice day.